So what we're doing today is a little bit more on the structure of matter here. Trying this with a little bit smaller of a pencil line there, a little thinner, so that hopefully I can fit some more of this stuff in here, because in a bit I'm going to have to draw a chart and got to kind of squeeze some information in it. So anyway, the original version of back when people knew they were positive charge and negative charges was they called it the plum pudding model, and essentially you basically just had this glob, whatever would be the plum pudding, that was this glob of stuff that would be this positively charged, just big glob of stuff, and then around, spread inside that positive charge stuff, would have been smaller little negative charges. Those were your little electrons, and they just were kind of in there inside this whole glob stuff. And this was the idea, the original ideas of the atom. But eventually, an experiment came along, the gold foil experiment, done by Rutherford, Marsden, and Geiger. And what they basically did is they put this detector around, and then they took this real thin sheet of gold foil, like literally like an atom thick. They could make it extremely thin. And then what they did is they fired particles at it. All right? And if memory serves me, they were alpha particles, which you should know what those are. And they expected that as these alpha particles went through, that they'd get near this plum kind of pudding, and they would get scattered a bit. So that some would go over here, some might make it straight through, some would come over here, and they would just kind of scatter in front, and you'd get these detections on that side as these alpha particles came in. But to their amazement, what they found is that sometimes what was happening is, and it wasn't often, most of the time they were going through, but occasionally as this beam would come through, you'd get one that would get reflected back like that. It wouldn't go through, it would actually bounce back the other way. And so this kind of threw this whole idea of this whole plum pudding out. It was like, well, that doesn't seem to actually fit what we have here, because occasionally we have these ones getting knocked back. So what ultimately was developed was a different model, the Rutherford Bohr model, which was the idea that you instead had these really small little tiny centers to the atom, and they called this nucleus, where all the positive charge was located, and then around it you had little negative charges. And I think this is the model y'all are mostly familiar with. You had these little negative charges, and they said that these would just basically orbit around. No, that wasn't a great circle, but they would orbit around at these different distances way out, and that the atom was mostly empty space then. So that when these alpha particles came through, they could pretty much just pass right through, usually maybe get slightly deflected. But whereas this little plum pudding model couldn't cause these to bounce back, if one of those alpha particles got near enough and actually had a collision with the very dense nucleus where most of the matter was contained, in all the protons and neutrons, that then it could hit and bounce back. And this kind of model would better explain what we see here. And it basically led to our main idea of an atom, which basically says that it is mostly empty space, so it's mostly empty. Most of the mass is right in the center, and I mean most of the mass is in the center. And when I say the center, I mean somewhere around 10 to the negative 14th meters in like the center, down in a little radius on that scale. And then the electrons orbit around. Electrons, they orbit. Kind of like how the planet orbits the sun. Now we know that this model, I guess we should say, this model doesn't fully explain everything we see, and it doesn't quite fit with what we know. For example, this kind of just circular orbiting, like what we see with the planets, actually wouldn't hold the electron together. All the forces we know that act on it just wouldn't work. So there are updates to this. You probably learned about them in chemistry, where you had the electron clouds, and you had the s orbital and the p orbital and things like that, which we'll talk about later. But essentially, this was the first model that kind of showed us that it was mostly this empty space here, and it put us on the kind of right track towards where we needed to go. All right, so that was the basic idea for this basic structure. But then, what are these particles? What makes them up? And it turns out we have a breakdown. We have two basic types of particles. All right, of all the particles we know of, we basically have two, and they are fermions and bosons. Okay, now bosons, these are typically your force particles. These are your force particles. These carry the force, which we'll talk about more in a minute. These are the ones that carry the electromagnetic force, gravitational force, allegedly, all these other forces that hold the nucleus together and things like that. So you had, just all of particles, and you have bosons and you have fermions, and then the biggest, and these over here, these are your matter. This is your matter particles, things that make up the nucleus. These are your electrons and things like that. They're under the matter particles, and the big difference is there's something called spin. It's a little bit of internal angular momentum that these guys have. It's not something you strictly need to know about at this point, but all fermions have a half integral spin, right? They have these half integral spins, and bosons have integer spins. I'll put it over here, just like 1. And sometimes you can hook fermions together, so a half and a half, and it'll become a 1. But basically, you have this. These guys, if you've ever heard of it, are not bound by what is called the Pauli exclusion principle. These guys are bound by it. It's that idea that you can't have more than 2 fermions with the same set of quantum numbers. It's why when you go back, if you've had your chemistry, you can't put more than 2 electrons per orbital. So like if you look at the s orbital, you put 2 electrons in. One of them is an up spin, one's a down spin. And then you can't put any more in there, because to put any other in there, they'd have to be another up half spin or down half spin, in which case it'd have the same set of all these quantum numbers, which we'll talk more about later too. But that's the idea here behind these fermions, and then there's bosons. And so breaking down fermions a little better, we get 2 basic distinctions here. You have leptons, and then you have hadrons. All right. So leptons, this contains your basic particles, a few other little particles, but it's your electrons and it's your neutrinos. I'm just going to put the symbol so I don't run out of room. Your electron, and there's some other particles in there too. Hadrons, these are the guys that are made up of quarks. Okay, so these guys are made of quarks. Okay, quarks. And then you have your 2 basics from there. You have what are called mesons, and these guys are made up of 2 quarks. And then you have your baryons that are made up of 3 quarks. I'm just putting Q for quark for right now. There are a bunch of different types of mesons. I don't have to really get into those. Baryons, there's different types of baryons, but the big one that y'all are going to be used to knowing is nucleons. All right, these are your protons and neutrons, basically, and they are made up of 3 different quarks. Okay, and these quarks that I'm talking about, they're very fundamental little particle. They don't break down anymore, and they're kind of like little cousins of electrons. All right, so we can break down the nucleons. We can say, oh, they're made up of quarks. Well, electrons and quarks, well, what are they made of? And as far as we can tell, they don't seem to be made of anything. And so, it kind of leaves us stuck there. So let's talk a little bit about quarks. I think you know about neutrinos that are already little neutral particles with practically 0 mass. And then electrons, about, they orbit the atom. They have that negative charge. If they're positively charged, it's the anti-electrons, the positron. But what about these quarks? Well, it turns out that quarks come in what are called flavors, different flavors, and there are 6 different flavors. different flavors, which basically means there's 6 different types. And these types, they gave them some fun names. They didn't go naming them boson, hadron, all these kind of crazy names. They named them things like up. They named them, let's see here, up, down, charm, top, bottom, and my favorite, strange. All right, so these are the 6 different types of quarks that you can have. And these different quarks can each have different types of charge. Now, we had talked before about a proton and electron having what is known as the fundamental charge. It was a charge that we couldn't break up any further. It was that one charge of an electron, and we would even denote it with this little E symbol, and if it was E plus, we were talking about a proton's charge, and it was 1.6 times 10 to the negative 19th coulombs, I believe, and you couldn't break it down any further. Well, it turns out here with quarks, they don't have the fundamental charge. They actually have what appear to be fractional charges of that fundamental charge. But the interesting thing is, it works in such a way that it always adds up to an integer charge. So, quarks, they always combine to make an integer charge. Okay, they always do. That's very important. Pretty much, if you can think of a way to add all of these together with their fractional charges, then you will have basically probably come up with a likely hadron, or a likely hadron, something that actually exists where you could do that. So I'm going to give you an example here. All of them have to either be 2/3 or 1/3, either positive or negative. So let's just look at an example, probably the best thing to do, and let's look at a proton. A proton is made up of 2 up quarks, up, and a down quark. And it turns out that for an up quark, you have a charge of 2/3 of the elementary charge. Not 2/3 of the coulomb, but 2/3 of the elementary charge. And for a down quark, you have a minus 1/3 charge. And that would be, again, minus 1/3 of the elementary charge. So if we look at this, if we come over here, we have an up and an up. That's 2/3 plus 2/3, and then a minus 1/3. And when you do 2/3 plus 2/3 minus 1/3, what do you get? 1. So that would be the charge of an electron. If you wanted to put the little elementary charge symbol here, 2/3 of E, 2/3, negative 1/3 of E, then that helps too, because this is just one elementary charge. Another one to look at, it's pretty well known, is the neutron. And the neutron is made up of 1 up quark and 2 down quarks. And so if we do something similar, you have 1 up quark, which is a 2/3, and then you have 2 downs, which is minus 1/3, minus 1/3, and what does that give you? 0, which is the charge, and we put that on there. It's the charge of a neutron. So whatever you do, you find your little chart. I don't think you're not expected to memorize all the charges on all of these, but if it was given to you, you should be able to tell me what the charge on something is, or combine these in some way that gives you an integer charge. So what I mean is, you couldn't make a meson. You couldn't do something like for a meson, which is 2 quarks. You couldn't do an up quark. That would be not giving you an integer charge. It would be a 4/3 charge, and that wouldn't work. And same thing for baryons. You're not going to do an up quark combination, because that's 2/3, 2/3, 2/3, which would be what, 6/4 So where's that, 1.5? And so yeah, that's not going to give you this integer charge of either ones or zeros or something like that. So it just doesn't happen. I'm not exactly sure why, but it doesn't. And as far as these 2/3 and 1/3, I know I'd said before you can't break that down anymore. We'll talk later about how you can't ever actually get a quark by itself because it just doesn't work. Something called confinement, and we'll talk about that in another little video I have planned. But it's also possible that these plus 2/3 and minus 1/3 and all things is just kind of an averaging out. But maybe, maybe not. We're not entirely sure because most of this is done kind of indirectly. So let's go ahead and just try drawing you the picture of all the elementary particles, just so you can get a look at all of them. Again, this isn't something you're expected to have memorized or anything like that, but it's just something you can kind of have. You really have to basically know how to read it. And so the first little thought here is it's just 16 of them. 16 of them. So I'm going to try and draw this where it's decent. Maybe I'll move this down a little more. So there's 16 of them. Okay. Let me undo that. So it's 4 by 4. And there's a better picture of this in your books. But basically, there's a nice division right here. And there's a division right along here. Okay? And so what you would have here, for example, would be an up quark. And you'd have your name would be listed here, the name of the particle. And then you'd have the mass of the particle, and then the charge of the particle, and then even though you don't really need to know it, a lot of times you'd have the spin listed right there. So it would be mass, charge, spin. So like we said before, this would be an up quark, so this would be a little 2/3 written here for the charge, and it would be the charge of the elementary particle of it. And then after that, you have your other quarks. I bet you can guess what these ones are. Charm, top, down, strange, my favorite, and bottom. And so these are, this little corner up here, these 6 are your quarks. So these are your quarks. Then over here, you have your leptons. This, of course, includes your electron. And then you have a muon and a tau particle. And then you have the little neutrinos. Electron neutrino. I believe that's electron muon, but you might want to double check me on that. And then your tau neutrino. And this corner here is your leptons, the little cousins of each other with the quarks. And then over here, you have your bosons. And so these guys, which we'll talk more about later, so I'm just going to write in their little symbols for the moment. Your bosons, sometimes called your gauge bosons, with a G, G-A-U-G-E, gauge bosons. And again, like I said, we'll come back and look at this. I just wanted you to be familiar with this chart, but as we continue going through this, these symbols and stuff I wrote here should become more familiar, but I don't want to spend a lot of time going crazy on it right now. But by the time we finish with this whole section, you should basically understand how this chart is arranged. And so this little column over here are your bosons, your other type of matter particles. This left side, These are your fermions, and these are then over here your bosons. Okay, that pretty much takes care of our little introduction to these elementary particles, and we'll talk more about them in future videos.